Hey there, this is Trinon with the CubeSat Flight Lab at the University of Michigan. We build CubeSats and Stratosats here, and we're hoping to post a lot of videos on this channel later on about how to build these things and also the flight hardware. We're going to start with this instructional video series about how to build a small printed circuit board around one of our chips that we use called the TPS2420. Excuse me if I'm not looking at the camera or speaking loudly enough. I haven't had a presence on YouTube since my parents posted videos of me doing the Rubik's Cube and playing the violin in middle school. But this TPS2420 name sounds very technical, but it's just simply a power switch, and we'll go through what it is, why we use it, and where we use it. So TPS2420 power switch, officially called integrated FET hot swap controller. It's this little chip that we use on our satellites to regulate current. Integrated just means that it is a small chip that goes on a PCB, and a PCB is a printed circuit board. It might look something like this. It is in your phones, your computers, your remote controllers, your blenders even. So it's everywhere. FET is a field effect transistor, and this is what's acting as a switch in our device. Hot swap means that this thing can sit in a circuit where power stays on, but you want to switch components downstream, and it can manage the inrush current that is pulled by that load downstream. And controller just means you're controlling the current that's going through it. So where do we use this? On our satellites, we usually have a dedicated printed circuit board that will regulate power from our power supply, which is usually our batteries, to different components downstream. It might look something like this. This is a board designed by one of our past GSI/engineers, Justin Schachter, who's working at JPL now. So to simplify, this board has some battery terminals right here on the right, and then there are 3 voltage rails, a 5-volt rail, a 3-volt rail, and then a battery voltage rail. And on each of these rails, you may not be able to see it, but there's this very small chip right there that's actually the TPS2420. A better look at it is to look at this board, designed by Texas Instruments. It's an evaluation board for the chip itself, and the chip sits right here, so you can really tell how small it is, about the size of my fingernail, or a fourth of it. But why do we use it? So when we have components, they can draw an inrush current when they're powered on, and this device can regulate that. It can allow that amount of inrush current, but if it keeps pulling that high of a current, then it's going to shut off and prevent any more power from flowing to that device downstream. In addition, if you have a set amount of current or a max current you want to run through a certain voltage rail, this device can do that also. So you can program it to say, hey, if the power or if the current goes above this amount, then shut off, don't let that device pull any more current from our power supply, which is our batteries, which is very good because then we have enough power for other components and also make sure that our batteries don't get destroyed from overcurrent or anything like that. Okay, so this board that we're designing is supposed to be for our students to learn about this chip that we always use on our satellites and also on their Stratosats. They want to test with it, see the current functionality, see how to turn it on and off and things like that. So we want to make a board that is easy to understand and students can learn and maybe even place the components on later on. So designing around this chip. This is a small design note that I have to see how we should put components around this TPS2420, this power switch. This is a device using QFN package, and QFN means quad something, I'm not sure, but it looks approximately like this up here. It's just a little like flat cube basically with pins underneath on the side, as you can see. And there are 16 pins in total, and we'll go through what we're doing with each of those pins. So since current or power is running through this, there's an input power on the left right here, 4 pins, because the more pins, the more power. And on the right, there are 3 output pins for this downstream components. And then there are a couple more important pins that we should talk about. So enable. This is an enable pin, so it enables or disables the device. So if we just block out this little extra part right here, if this pin is pulled to ground, this device will be turned on. So it's inverted logic. We want to power this, or we want to switch this on and off using a Raspberry Pi in the future. So we added a MOSFET to make sure that the Raspberry Pi can drive this pin. If the Raspberry Pi pulls one of its GPIO pins high, it will enable this MOSFET and then pull this pin down to ground. If the Raspberry Pi pulls the G power pin logic low, it will disable this MOSFET and then leave this pin floating, and therefore the device is off. Fault and power good are two pins that will tell you whether it detects a fault, so an overcurrent, or it senses that the power is completely fine, no overcurrent is detected. And I'll talk to you more about that later. IMON is a current monitoring line, so I is current, MON is monitoring. It's used to monitor how much current is running through this power switch, and we can extract how much current is running through using a mathematical formula involving this resistor right here and detecting the voltage on that line. CT is used to program the timer, so this is a fault timer, and this device will allow a little bit of overcurrent, but if the overcurrent doesn't go down by the fault timer, by the time the fault timer expires, then this device will shut off. This is to allow a certain amount of inrush current when your components power up, but no more after that. And we can set how much time we allow it to go using a capacitor, CCT. iFault and iMax are the two pins that are used to program the maximum current allowed, and they serve slightly different functions. So iMax is the absolute current limit. If you pull current more than that, it's going to immediately go into current limiting mode and not allow you to pull any more current until you decrease the amount of current drawn. iFault is the limit over which you will have to decrease your current by the time the timer expires. So if you have an iFault of 1 amp and you pull 2 amps, then you have to make sure that your 2 amp draw go below 1 amp by the time the timer expires. Otherwise, this device will shut off and you can't pull any more power from your source. Latch is what it will do in the case that it detects a fault. So if it sees that there's an overcurrent event, then it will latch off or retry again and again. So let me explain that a little more. Say your device downstream pulls 4 amps and this device will only allow 1 amp through. It's going to turn off, shut off immediately. But what it does after that will depend on this pin. If you close this switch, then this device will just stay off forever until you power cycle it. So you take off VIN and you put VIN back in. Or you can turn enable off and turn enable on again. If this latch pin is not pulled to ground, then the device will automatically retry. So you don't have to power cycle at all. It will just automatically retry and keep trying again and again and again until your current goes beneath the current limit. And then this is just a ground pin. So pins 14 and 15, I skipped over that slightly, but these are your fault and power good pins. These pins will be used to show visually whether the device detects a fault or it's operating nominally. So fault here, and power good, I expanded it below here because there was not enough space. These two diagrams are the same, by the way. Basically, these are pulled over to LEDs on the right side, and you can examine the circuit a little more on your own time to see how it works. But basically, these pins are open drain, so when it detects a fault, then it will pull fault to ground. If the power is good, then it will pull power good to ground. So therefore, if it detects a fault, this red LED should light up, and if it is nominal, nothing's happening, then this power good LED, this green LED should light up. Okay, so now that you have a brief understanding of how this chip works, we're gonna go on to design it on Altium, and then ultimately print the circuit board, order it, place it, and then test with it. Okay, see you.